these are the functions I'm going to use to demonstrate how we use these particular rules, these inverse trig integrals. But before we get started, I just want to make a note that those particular fraction integrals work using the inverse trig and these ones don't. So it's not enough to just see a fraction and then go, oh, it's going to be one of the inverse trigs, because this particular one here actually integrates to a logarithm, this one integrates to a power function, and this integrates to a mixture. So if you want at the very end of the video, I'll give you the answers to these ones, just out of curiosity for yourself. But what you've got to actually do is recognize that it fits the format very closely of a number on a square root of a number minus something squared, or a number on top of a number plus something squared. And if it fits those guys, then we use the trig integrals, inverse trig integrals. Let's do these. This one, if I check my sheet, fits pretty closely into this format here, the inverse sine of f of x on a, but I don't have f of x squared. So the first thing I'm going to have to do is fiddle and think of this whole thing as a perfect square. And if I pull it out like that, that looks pretty good to me as the same as what it was above. But I really want a 3 on top, and I've currently got a 1 on top, because 3 is the derivative of this. So I'm going to throw a 3 on top, and I'm going to throw a 1 on 3 out the front to make it balance. So this bit now fulfills this, and I just carry my third down. A was 1, so it stays like that. This one fulfills this particular rule here. We have a number on the top, number here, and something being squared here. Just a quick note, the f dash of x that's sitting on top here is not the derivative of this whole piece at the bottom, because that would be 8x. It's the derivative of the inner function that is being squared. So when I pull this into looking like that, so that's the one I'm going to do first. Actually, just pull the square out of the 4 as well. The actual inner derivative is just linear. Now it doesn't matter to me that there was a 3 and I want a 2. What I'm going to do is the 3 is a multiple of this, so it can actually just pull out the front. And I'm going to put my 2 on the top, and then because I introduced the 2, I'm going to balance it off. If I introduce a number to the bottom of a fraction, I'll balance it off on top. And if I introduce a number to the top of the fraction, I balance it underneath in the fraction that I put out the front. And any number that's in the way, I just push forward. That's the basic rule, I think, of integrating anything when you know what you want to make it match to. I always make it match on the inside and then push the numbers around out the front. That push around number comes out the front, and then I've got a being 1 and f of x being 2x, so I'm ready to go with inverse tan of 2x plus c. Using the same approach I used before to get the f of x squared in this one, I can say that's root 3x squared. So it doesn't matter if you don't have a square number. Now I want a root 3 on top. So put a root 3, put a 1 on root 3. Now we'll go into 1 on root 3 inverse sine of, look at my rule, f of x on a. There's actually an alternative method we can use here. If we want to fiddle with the numbers in a completely different way, what I could do is actually factorize my 3 out of the bottom. Yes, it's not a factor of 1, but if I times it by 1 on 3, I get back to 1, and say that. Do you see how I can actually factorize any number out of any set if I want? I can pull that number forward and just put in what it would expand to get back to where I was. That one, you always need your dx, because down the track you might be integrating with different variables. That's 1 on root 3 squared. And that one will work like that, where I don't need to put an f dash of x on top, but this 1 on root 3 can actually just come out the front because it is a factor of the whole thing. And now I have an a squared minus x squared. I think this method's harder, but I just wanted to show you in case that you're comfortable with it or it works at some time that something else doesn't, and just to show you what you're capable of with your algebra. And that one will go to the inverse sign again. So the 1 on root 3, inverse sign. This time the f of x is x, and the a is 1 on root 3, so that actually divided by 1 on root 3 is the same as timesing by root 3, and we got to the same answer. As promised, here are the solutions to the other ones. Send me an email if you want me to make a video on this.